everyone. In this video, we are going to learn about the equivalence relation and the equivalence classes. Let's start with the definition of equivalence relation. Let's suppose a relation is defined on a set A. That relation is called as a equivalence if it satisfies the three conditions, that is, relation is reflexive, symmetric, as well as transitive. Reflexive means every element is related to itself, means we have the ordered pair of this form for every element of this set A. Symmetric means if we have the ordered pair A, B as a part of a relation, then a reverse ordered pair must be there. Transitive means if A, B is a part of a relation as well as the ordered pair B, C is a part of relation, this implies the ordered pair of the form A, C should be there to call it as a transitive. So if all these three conditions are satisfied, then the relation is called as an equivalence relation. In equivalence relation, if we take the two elements and they are related with each other, then we call them as a equivalent. And we are using this notation. This means A and B are the equivalent elements with respect to the equivalence relation. Let's understand with the help of example. Suppose we have the set that contains the four elements 1, 2, 3, 4, and the relation is given in this form. On the set A, we need to check whether this is an equivalence relation or not. First thing, we need to check whether this is a reflexive relation. Reflexive means every element is related to itself. So there are four elements, means every element from this set is related to itself. Is it is there? Let's check it. Ordered pair 1, 1, ordered pair 2, 2, ordered pair 3, 3, ordered pair 4, 4. So it means every element is related to itself. So hence it is a reflexive. Now for the symmetric, means if any ordered pair is there, reverse ordered pair must be there. For these ordered pair, it reverses itself. Even in this case, it reverses itself, it reverses itself, it reverses itself. So there is no need to check for this one. Now check for this. 1 is related with 3, 3 is related with 1. It means reverse ordered pair is there. 2 is related with 4 and here 4 is related with 2, means reverse ordered pair is there. So hence it is a symmetric. Now check for the transitive. For transitive, the best way is always start from the non-equal elements. Why? Because if you take the equal elements in an ordered pair, operate with any non-equal elements, suppose here we have 1, 3, you will get the same ordered pair in this case. So when we have the equal elements in an ordered pair, it acts like a mirror for the other ordered pair, provided if you are finding the transitive form. So let's start from here first. 1 is related with 3 and 3 is related with 1. Ultimately, we are getting a 1, 1 as ordered pair and it is there. For the next case, 3 is related with 1 and here 1 is related with 3. So you will get the 3, 3 as the ordered pair and it is already there. 2 is related with 4, 4 is related with 2. Ultimately, we are getting 2, 2 and it's there. 4 is related with 2, 2 is related with 4. So we have ordered pair 4, 4 and it's there. So it means it is a transitive relation. So as the relation is symmetric, transitive and reflexive, so we can call it as the equivalence relation. Let's take one more example. Here we have taken the set that contains the four elements 1, 2, 3, 4 and the relation is defined as A is related with B. So we read it as the element A is related with the element B with respect to the relation R. So it is also written in the form of ordered pair AB that belongs to the relation R. If and only if 2 divides A minus B. This is the symbol for the divide. Means When we say that 2 divides A minus B, another way to write this one as A minus B is divisible by 2 means we are getting some integer here, where K is any integer. Now we need to check whether this relation is equivalence or not. So first let's identify what type of elements are there in this case. Now pick any two pair, make sure their subtraction is divisible by 2. Now if I take the ordered pair 1, 1, whether that is divisible by 2? Yes, because 1 minus 1 is 0 and 0 by 2 is equal to 0. So it means 2 divides 0. And that is also applicable for the next element. It means ordered pair 2, 2 is a part of relation. So similarly, we can say that ordered pair 3, 3 and 4, 4 are the part of relation because their subtraction is 0 and 2 divides 0 means 0 by 2 is 0. Next ordered pair is possible as 1, 3 and 3, 1 because its subtraction is minus 2 and 2 divides minus 2. Its subtraction is 2 and 2 divides 2. Next ordered pair is possible as 2, 4 and 4, 2. Its subtraction is minus 2, that is again divisible by 2, and its subtraction is 2, again it is divisible by 2. No other ordered pair is possible in this case. So it means we have these ordered pair in the relation R. As you can observe, we have already done that. This is the equivalence relation in the previous example. With the same procedure, we can say that this is an equivalence relation. Here we have taken the next example. Let R is a relation that is defined on the set of real numbers such that A is related with B if and only if A minus B is an integer. We need to check whether R is an equivalence relation or not. In the previous case, we have the finite set that contains only 4 elements and it is very easy to identify here. But in this case, we have the set of real numbers. Directly by taking these ordered pairs in a relation, we cannot say that it is an equivalence relation. So we need to check it in a general way. How to do that? First thing, we need to check it for the reflexive. For reflexive, we say that we have the ordered pair of the form AA for all values of A belongs to the set of real numbers. Here we have taken the set A as the real numbers. So if this relation contains this ordered pair, it means it will satisfy this condition because the requirement for the relation is A minus B must be an integer. So for here we can write because A minus A is equal to 0 is an integer for all real numbers A. So we can say that A is related to A for all A. Hence R is reflexive. Now for this metric, suppose ordered pair AB is a part of relation. It means A minus B is an integer as per the requirement. If A minus B is an integer, so B minus A is also an integer. This implies BA is a part of relation because it is an integer as per the requirement. We have fulfilled that. It means it is a part of relation. So it means R is symmetric. Now for the transitive. If AB is a part of relation and ordered pair BC is a part of relation, it means A minus B is an integer and b minus c is also an integer. So we can write a minus b plus b minus c. We can add them because the addition of two integer is again an integer. On the left hand side we are getting this form, and on the right hand side we can say that is an integer. So this implies a minus c is an integer. So if a minus c is an integer, it means a c ordered pair is a part of relation and hence R is transitive. So if R is reflexive, symmetric, transitive, so we can say that R is an equivalence relation. In this case, we need to know one more term, that is a congruence modulo M, because it is quite related with the equivalence relation. Congruence modulo M means, suppose we have any integer M where M is greater than 1, the integer a and b is called congruent with respect to this mod M if M divides difference of these two. Let's understand with the help of example. If I write 21 is congruent to 15 mod 2, whether this is correct or not, it means we need to check whether 2 divides 21 minus 15. 21 minus 15 is 16. So this implies whether 2 divides 16, yes. It means this congruency is correct. And if I write 14 is congruent to 3 mod 5, whether this is correct, means we need to check whether 5 divides 14 minus 3. 14 minus 3 is 11. Whether 5 divides 11? No. It means 14 is not congruent to 3 with respect to mod 5. It is very simple to calculate whether the two terms are congruent with respect to mod M or not. What we can do, we can find the remainder. When this 21 is divided by 2, remainder in this case is 1. 15 divided by 2, remainder is 1. If both side remainders are same, then we can say that these two terms are congruent with respect to this number. Like in this case, when 14 is divided by 5, remainder is 4, and here we cannot divide 3 by 5, so it means its remainder is 3. Both side remainders are not same, it means they are not congruent. Let's check it whether this is true or not. 143 is congruent to 11 mod 3. So one procedure is you need to check 3 divides 143 minus 11 or not. This is equal to 3 divides 132. So yes, this is divisible. Now you can check it from the remainder as well. 143 when divided by 3, the remainder is 2. 11 when divided by 3, remainder is 2. Both side remainders are same. It means they are congruent with respect to modulo 3. Now note that the relation R, where we are taking the ordered pair AB such that A is concurrent to B mod M, is always an equivalence relation on the set of integers. The proof of the statement will be uploaded in upcoming videos. But here just remember that the congruence modulo M forms the equivalence relation over the set of integers. Let's take a brief overlook on this one, why it is an equivalence relation. For reflexive means we have the ordered pair of the form this. So it means in this case we will replace it as A is congruent to A mod M. Divide this number by m. Whatever the remainder we have, the same remainder we will get on this side. It means they are congruent. It means relation is reflexive. Now for the symmetric, if A is congruent to B mod M, and if I write B is congruent to A mod M, whether there is a change in this case, check it whether the remainder is same or not. When A is divided by M, suppose the remainder is K. As we are saying that they are congruent, it means in this case when B is divided by M, remainder is again K. So when you shuffle this one, B is divided by M, remainder will be K, and even in this case the remainder will be K. So there will be no impact on the remainders. It means they are congruent, and hence we can say that the relation is symmetric. Similarly, we can think for the transitive. So if I say that A is congruent to B mod M and B is congruent to C mod M, can we say that A is congruent to C mod M? Just check whether there is a change in a remainder or not. As in this case, we are saying that A is congruent to B mod M. It means here remainder is same, let it be a K. So same thing we are taking in the next case, B is divided by M. So in this case, remainder is K. As they are congruent, again it means here remainder is K. So here we are getting a remainder K, even in this case remainder K, means in these two cases same remainder is there. So hence it is a transitive also. So this is just a brief overlook over this one, but the proof is little different. That will be uploaded in the upcoming videos. Next we have equivalence class. Suppose we have the equivalence relation on the set A. The equivalence class is defined for the element of the A. So we can say that equivalence class of A is set of all elements that are related to element A. It's a very simple. Suppose we have this example, and this example indicates that R is a relation, that is an equivalence relation on the set containing four elements 1, 2, 3, 4. In this case, we need to find the equivalence classes, and after that we need to predict how many distinct equivalence classes are there. So total number of equivalence classes is equal to the number of elements in a set. So total elements are 4. So it means we have 4 equivalence classes in this case. As the equivalence classes is represented by this form, or we can represent in a simply square form. Equivalence class of 1 means collect all those elements that are related with 1. It's like we need to collect all the ordered pair 1, S. Then pick all S in a one set. That will give you the equivalence class of 1. Now 1, S, that is 1, 1 and 1, 3. The value of S in this case is 1 and in this case 3. Put it in a one set, that is the equivalence class of 1. Similarly, we can find the equivalence class of 2. So collect the ordered pair of the form 2 into S. So S value in this case is 2. 2 into S form is here. It means the S value in this case is 4. Collect them in a one set, that is the equivalence class of 2. Now read the sentence again. Set of all elements that are related to the element A, that are related with the 2. Now in this case, collect all the elements that are related with 3. So 3 is related with 3. 3 is related with 1. It means we are getting this set. For the 4, 4 is related with 4 and 4 is related with 2. Now this is a set. Either write in this form or you can write in this form. There is no difference. Even in this case, we can write it as 1, 3. Now we have 4 equivalence classes. Point is, how many distinct equivalence classes we have? Check it. Equivalence class of 1 and equivalence class of 3. Both are same. So in this case, equivalence class of 1 is equal to equivalence class of 3. And equivalence class of 2 is equal to the equivalence class of 4. In this class, we are getting a 2 elements, that is 1, 3, and here 2, 4. It means we have 2 distinct equivalence classes. Also note that 1 is related with 3 and their equivalence classes are same. Here 2 is related with 4 and the equivalence classes of 2 and 4 are same. So based on this, we have one result. The result is, if R is an equivalence relation on the set A, then the following statements are same. It says that if any element is related with second one, then their equivalence classes are same. Like in the previous case, equivalence class of 1 and 3 was same, that is 1 and 3, and equivalence class of 2 and 4 are same, and they contain the element 2, 4. So if any element is related with the second one, means if A, B ordered pair is a part of relation, then their equivalence classes are same. And if their equivalence classes are same, it means that intersection is definitely non-empty. What is the intersection of equivalence class of 1 and 3? That is equal to 1, 3, because both are containing the same element and hence it is non-empty. Based on the concurrence modulo, we can also find the equivalence classes. Here we need to take the concurrence modulo 4 and we need to write the equivalence class of 0 and 1. Before coming to the 0 and 1, just remember, for the concurrence modulo m, collect the remainders. Like in this case, we are taking concurrence modulo 4. So what are the remainder possible in case of 4? Remainders are 0, 1, 2, 3. So these are the 4 distinct equivalence classes we have. And if I say what is the equivalence class of 4, that will be similar to the 0, because when you divide 4 by 4, remainder is 0. They are related with each other, hence their equivalence classes are same. Similarly, equivalence class of 5 is similar to the 1 and equivalence class of 6 is equal to the equivalence class of 2. Equivalence class of 7 is equal to the equivalence class of 3, and same for the others. But in this case, we need to find the equivalence class of 0 with respect to congruence modulo 4. So what we need to do in this case, collect all the elements of the form 4k, means we need to collect all the integer of this form, because when we divide this with 4, we will get the remainder 0. So what type of elements we are getting in this case? 0, 4. 4 when divided by 4, remainder is 0. 8 when divided by 4 is 0. 12 when divided by 4, remainder is 0. So collect all those elements in a one set. Its previous one is minus 4, minus 8. So collect them in a one set. So this will give us the equivalence class of 0 with respect to modulo 4. Now what is the equivalence class of 1 with respect to modulo 4? It means we have the element of the form 4k plus 1. So what are the possible integers when divided by 4? Remainder is 1. That is 5. Then 9, 13. Continue this. Basically their difference is 4 and they are form of 4k plus 1. So we can write 1, then minus 3 and continue. Collect them in a one set, that will give you the equivalence class of 1. Similarly, you can write the equivalence class of 2 and 3 with respect to congruence modulo 4.